is about a 10-15 seconds below.
In the YouTube. Yeah. Mm-hmm.
Okay, good morning. First Sunday of the month. Always a chai and wine at Prithvi Theatre. Today we are not at the theatre, we're at Prithvi House. There's another event happening there. But we still have a very, very exciting program for you today. So for those of you who are watching online, please note that the only way we can interact with you is via the chat. So please put your questions and comments in the chat and we will relay them to the presenter, Piyush. So let me get started and introduce Piyush. So, I mean, he's a famous guy, you can Google him, but I won't get into all that. We are delighted that he has decided to come to TIFR, and this is his second January already. Piyush did his bachelor's in computer science from IIT Kanpur, went to Berkeley for his PhD, went to Caltech for a postdoc, and then eventually we could snag him and get him. We're very delighted. So he works in the area of probability theory and applying that to computation and looking at this. So it's a little bit mathematical, algorithmic way of looking at computer science. And he's also a delightful storyteller. And hopefully he has going to tell us today about approximations, because in reality, you know, the world is too complex to get everything exactly done. And often approximations are what really allow you to make sense of things. And how have they progress through history till today, till what we do, is what he plans to tell us about. So let's listen to him. So now you can start sharing your screen. We need to just do this for the online audience. I'll just check that it's happening and then you can go ahead. Okay. Just give us a second till I can see the. I'm seeing it on Zoom. And I am seeing it on YouTube. I'm seeing it on YouTube as well. Yes. So I think we are good to go. If anybody asks questions on YouTube, I will decide whether I should interrupt you or keep it for that.
Yes.
You guys, of course, not only get a chance to listen to all of this and go back and listen to it on YouTube if you'd like, but you also get chai and you get a chance to answer more questions after chai or ask more questions after chai. We answer them. So we are live, right? And we're on. Okay, all yours.
Okay, yeah, thank you, Arnab. So thanks for coming. Welcome. So let's talk about approximations, and let's start by
because the mic is only for the online audience.
Yeah. So let's start by trying to put square pegs into circular holes, or the other way around. And the first thing that happens is that we don't have the one. Yeah. So here is a problem that that somehow arose in a lot of ancient cultures. Probably still arises. You have a circle, so maybe a circular field. Sometimes it was a carpentry issue that people had a circular, like a container, and they wanted to make a square container with the same area on top. Okay, so they wanted to do this somehow. So yeah, so as I said, it's ancient. So here is one solution from a long time ago. So it says a square of side 8 has the same area, very confidently, apparently, same area as a circle of diameter 9. So I don't know, because I don't have the exact quote. This is from a paper which cites it to an Egyptian document from about 2000 BCE. Okay, so really long ago. So let's see if they were right or not, right? So their goal was probably like they were probably doing some field measurements, and like, it's very important that someone gets the same size of the field somewhere else, but in a different shape. So we all know that the area of a circle with diameter 1 is pi by 4. So this you might remember from middle school. If not, so pi is the number that you've all heard about, which is about 0.785 if you start writing it in decimal. And what they are saying is that the square that they are going to make will have side length 8 by 9. So the area will be 8 by 9 squared. And that looks like 0.791, not so bad, right? It's like 1% error or something, or much less than 5% error. Right? Really, really good. 2000 BCE already, right? Uh, so this is good. So people have done this for a while now. I mean, so the Greeks were interested in whether you can do this by using only rulers and compasses. So that it turns out cannot be done, but that we had to wait till the late 19th century, or maybe even later, slightly later.
You can just hold on for 30 seconds. The video is not
Yeah.
coming. I think I need to transfer the video to your laptop.
Okay.
I'm gonna put this.
Mhm. No, yeah. So
Someone turn on the video.
which video?
This video.
Huh.
Oh, that's right. Okay, good. Excellent.
But it is probably using the laptop video right now. Yeah, but that can.
Yeah, that can you change to C922. Oh, good. Yes, I think we have it. Okay, go ahead.
Yeah.
Sorry for that.
Yeah. So there's a question, which was that I said square of side 8, and then I very sneakily wrote 8 by 9 there. So this was about a circle of diameter 9. So that circle also has been shrunk to diameter 1. So the square also has to be proportionally shrunk to side length 8 by 9. Okay. So, but this already, so at 2000, in 2000 BC, already people were, so there are some nice features here. So firstly, it's wrong, right? It's not the right, like it's not exactly correct. But for their purpose, it was probably fine. And it is very easy. Right? That is very important. It could be done very quickly. Right? They didn't have a big computer to write down that thing. Here, yeah, 8 by 9. That potentially, even at that time, we could do easily. So this is an important thing about approximations. They have to be good enough, and they have to be at least reasonable, like in the sense of they has to be useful. So for the purpose it has to be useful, and it should be easily achievable. So the exact answer might be too hard, but here is what. So this actually kept on going. So I said many different cultures. So this is in Egypt. You have similar things from the Middle East around the same time, Babylon. You have from India and China, 3.1416 was around the same time, around 500 CE. That approximation to pi was known to Aryabhatta. Like very exactly, he wrote that, and he actually says the where he mentions the 3.1416, that so his exact phrase is that if you take a circle of diameter 20,000, its circumference approaches, that's the exact word he used, asan approaches 62832. So possibly he was aware that it's not exact, this can be improved. Around the same time in China, 3.14159, which is slightly better than 3.1416, was known. And of course, by now, pi can be approximated to any number of digits. But again, for different purposes, different approximation. So, but this is about a number, one particular number, this number pi that has to do with a circle. Usually, you don't have one numbers. There are many things you would want to approximate, a whole class of things. So here is another kind of question that many of the ancients are very much interested in. And this is to find square roots. Okay, so you have, so this is like if you want a square of a certain area, what should be the side length? So this is what they wanted, and they knew that some things are easy. If my square is of side of area 25, what is the side length? 36. But in between, you get like 29. Okay, so this is exactly the question they're asking. You know, 25 is 5. What does 29 map to? And here is a description from a manuscript that's called the Bakshali manuscript, after the village where it was found. This village is near Takshashila in modern day Pakistan. This manuscript is a raging controversy about when exactly it dates from. But almost everyone agrees that at least the contents are certainly at least as old as 400 CE. Okay, 400. And here is what it says. It says, In the case of a non-square number, so this is of course the script, the manuscript I think is in Sanskrit, but this is the translation. In the case of a non-square number, subtract the nearest square number, divide the remainder by twice its nearest square, half the square of this divided by the sum of the approximate root and fraction. This subtracted and will give the correct root. Of course, everyone understands perfectly well what happened, right? Maybe not, but let's at least convert it into our modern notation. This is what they're saying. So they're saying that if you are trying to find out the square root of a square plus b, so for us, let's say a is 5, so a square is 25, b is 4. So we are trying to do 29, let's say, right? So then this part is to do that a that you know, that original approximation, and add to it b by 2 by a. So b was 4 and 2 by a. Very nice rational thing that can be. In fact, this approximation was known to the Babylonians at least 2000 years before this. So the Babylonians were older at that time than they are to us. Right? So this is 1500 years ago, and Babylonians were about 2500 years before them. So this was known to them. These guys are saying, okay, you take what the Babylonians knew and subtract this. Okay. So again, like approximation. So firstly, again, one should ask, is it good enough, or is it even better? Probably the Babylonian thing was better, and this one actually just messes things up. Maybe it's better than the Babylonian one. So let's try this out. Okay. Any questions, by the way, so far? Okay, good.
I mean, a plus b by 2 is not bad for 5.3.
Yeah, so we'll see. We'll actually see. We'll see what kind of errors these two have. So today we can write code. So you write code, and here is what you do, right? I mean, everyone clearly understands everything, right? So you compute the Babylonian approximation, then you compute this Kali approximation, and you check what happens. So I did not do 29. I can do 29. Maybe after the session we will run the code on 29. Here is it for 10. Okay, so we are trying to do 10, square root of 10. So a is 3, b is 1, right? 3 square plus 1. So the Babylonian approximation is 3.16666. Pretty good, actually. In fact, there are old Indian texts which say that if you want to do pi, you just use root 10. And in fact, one of them, I think Bhaskara, calls it Sukhartam, in the sense that it's the easy thing or nicer thing to do. Why use this exact, all these 3.1416? Just use square root 10. But so square root 10 is not an unimportant number, it's an important number. And the Babylonian approximation says 3.166. Our closer cousins give 3.1622807, etc., etc. So, okay, and you square these numbers to see how good they are, and you see that the Babylonian thing squares to something like 10.03, and this one, at least the first 4 digits after the decimal are 0. So it seems like a better approximation, right? And in fact, if you look at it, so this is the correct answer. Correct answer as in computed by modern means, when like everything is known. So this can be more or less correct. If you square this, you will probably see an error only in the last few digits. And this one, let's compare these two. So the Babylonian one agrees till 2 digits. And how many digits does this one agree to? 4. In fact, okay. So this is an interesting thing, 2 to 4. So yeah, 2 to 4 is 4 is 2 plus 2 also, and it's twice of 2 also. So, but actually, what I like to say here is that actually this is what is happening. The Berkshire thing is going to give you 2 times as many good digits as the Babylonian. Okay. So let's also look at it for 2. Okay, so approximate square root of 2. This one gives 1.5, this one gives 1.1416. This, again, I guess many people remember from middle school something. And this is, again, 2 more digits. So it's reasonably good. Okay, so for those of you who are already getting bored, here's an exercise. So you show that this Berkshire method is actually just the Babylonian method applied twice. So basically what these guys were doing is they were taking the Babylonian thing, and they're being clever. So Babylonian thing is to take the current approximation, do b by 2a. But they're saying, okay, now we take this approximation and again do the same, this Babylonian step one more time. And this is what this is. So this is some algebra that you can do and show that it is. Okay, but I mean, does anyone have any idea how one will come up with these things? Like,
first one is completing square kind of.
Completing square.
A square plus b is already plus some b square.
Yeah, so if you square this thing, then this will look like a square plus b plus some b by 2a whole squared or something. And that is hopefully a smaller order error. So, but again, this is like very specific to the square root, right? And it's not clear if one can generalize all this. So, yeah, so after the fact, yes, we can justify this. And this one, I don't know how to justify like this at all. But from first principles, it's not clear what to do, right? And this was actually one of the important problems that occupied people, again, across several cultures. So the Bakshali manuscript is from, as I said, Takshila. The Babylonian method is from Babylon, Middle East. For some reason, somehow this became a very important problem, especially in Iran. For some reason, like a lot of the developments on this kept happening in Iran, and especially like in the really the biggest thing for doing all polynomials was by some mathematician called Al-Kashi in the 13th century. But today, what you can do is you can see all of these as a special case of something of a more general idea called Newton-Raphson method. Okay, so I'll say what this is. But any questions so far? No. So let's see what this Newton-Raphson idea is, and this is really the thing that what the unknown authors of the Bakshali manuscript, the unknown Babylonians, and Al-Kashi, etc., were finding special cases of over several millennia. So here is what the Newton-Raphson method looks like. So this is a video that I made. So let's see. So okay. So let's see. So sorry. So yeah. So what we are trying to do is to find an x such that this y becomes 0, right? We are trying to find the square root of 2, let's say. So we are trying to find an x such that x square minus 2 is 0, so, right? Y is 0. So again, like some class 9 or class 10 mathematics, you can draw graphs of these things. So I can keep changing x, which is viewing like here. So, and then I can keep plotting the value of y. And if I plot it, that picture looks like this. The curve looks like this. So what I really want to find is where does this curve intersect that horizontal line? The horizontal line corresponds to y equal to 0. So this is what I want to find. And I want to find the square root of 2, and my current approximation is 1, right? And I want to find a better approximation. 1 is not such a good approximation. So this is what the Babylonians wanted to do, right? So they started with a equal to 1, b is 1 also, and you want to get some better approximation. So what you do is the following. And this actually incorporates many of the ideas that are very important in approximation in other situations also. So you have 1, so you compute the value of y at 1. It is not 0. You want it to be 0, but it's not really 0, right? It's whatever, wherever this vertical line intersects this. So what is that value for y, for x equal to 1? It's minus 1. So if you draw this, it will be minus 1. At this point, what do you do? So which are the equations that we really know how very nicely to solve, like which you actually probably everyone solves several times a day, or at least a few times a day? Linear equations, right? If it's a line, then it's easy, right? If the cistern fills, if I put the tap at half open in 2 hours, if full, if the tap is full, then it will fill in 4 hours, right? No. 1 hour, right? So okay. So okay. Anyway, so what you do is you say, okay, let me forget about this curve and let me just draw a straight line here and try to solve the straight line equation. Okay. So this is what you do. So you draw the straight line, but which straight line? So which straight line do you draw? So the straight line should have something to do with that curve. So it should really like around that point, it should look really like what the curve is doing. Right? So it should be touching the curve essentially. So this fact that what it means for the line to be touching the curve, this actually is a pretty serious thing in the sense that it's not obvious. It's obvious maybe in hindsight, but it took people several as millennia to really get to grips with this notion of a line touching the curve and then going somewhere else. But anyway, as long as we have some intuitive understanding of what this touching the curve means, we can draw that line, and wherever that line hits is our next guess. Okay, so if you do this once, you start from 1, you go to the curve, and you drew this line thing and get to the point. If you do it for this one, you will get the Babylonian method. Okay. But this is a general procedure. This curve did not have to be the x square minus 2 curve. It could be some other curve also, and you could do this process. And that is the Newton-Raphson procedure. So the Newton-Raphson procedure applied to this particular problem gives you the Babylonian approximation. Of course, this is probably not how the Babylonians came up with it. They probably did what was mentioned here. But this is a more general. So this idea of generalizing things is quite important here. And so Newton-Raphson. Okay. Yeah. Okay. So the Newton-Raphson method is for any general curve. The curve need not be this, and applied to the square root function. One step gives the Babylonian method. Do it twice, you get the Berkshire method. Okay, and you can keep doing it more. And the thing I said about this doing twice is a general feature of the Newton-Raphson method. So if things are nice, and they are nice for the square root function.
Can you just explain how does it happen?
What happens?
Applied once translates into
yeah, so you because you can write down my equations, right? So this is my A. I compute this point y at so a square minus 2. Then I compute what this line looks like. Okay, this tangent line. And then if I know the line, I can easily figure out where it intersects the axis. So line solving equations is easy. So, and when you do this whole calculation, you see that then this point will exactly correspond to that a plus b by 2.
Step 2, I will go from that.
Yeah, in step 2, you will go from this point. And you will go up to this. Yeah, you'll go up, and you will draw the tangent at that point, and it will hit again the x-axis at some point, and that will be your next guess. And that next guess will turn out to be the Berkshire.
But did Berkshire folks get this?
Probably not. I mean, so I don't know what they probably. Yeah, so the thing is that so we think of algebra now as this letters and manipulating this. This is not how algebra was done. Even 300 years ago, apparently, this is not how algebra was done. Algebra was done by let's take this quantity and add it to 4, and then the previous quantity and multiply that by 5, and then add the 2 preceding quantities. So this is how people would talk about things. So things like this were maybe not so easy to do. I mean, like notation helps, and but yeah, you would imagine that if a lot of money, etc., was on the line, then someone or other would have done the work, and that's how probably this manuscript. So it's kind of interesting, like because a lot of original, like when you look at mathematics from that era, often it was not developed as mathematics as first. Maybe in Greece it was, but especially in India and Iran, it would be like either for astronomy, like mostly, like most of the most advanced things were for astronomical reasons, like you want to calculate some orbits or something like that, or for things like this, like measuring ground or like Newman, etc. So there is always this notion of where the problem is coming from. Okay, so this is Newton-Raphson, and so okay, so some timeline. So Babylon, 2000. So that approximation is probably from 1000 BC or before 2000 BC, something like that. The Berkshire manuscript is probably from around 500 CE or around that period. And Newton and Raphson are from 1700, something like that. And in between, there are people like Al-Kashi, etc., 1200. It's a millennia long adventure which has come to this. Okay, any questions so far? Yeah.
Assuming that you're taking a lower bound and an adding, can you not take, for example, 0.25?
Yes, yes. So this picture tells that it can do the other way around also. Yeah. So again, so what I should also say is Newton-Raphson looks like a Penake. It's not. It's like you have to be somewhat close to the answer. If you start far off of the answer, it gives other nice things. It starts doing very chaotically. It can go all over the place, and you might have seen these pictures of various so-called what are they called? These chaos pictures. Okay, I'm forgetting the name, but like these pictures of in the plane with like lots of colors and like behaving in a very random manner, but looking quite nice. Some of those pictures are generated by just running the Newton-Raphson method and seeing where it's finally ending up. So even changing it by a little bit, if it's close to the boundary, can completely change where it will end up at the end. So Newton's raphson is good provided you give it a correct initial guess. And if you give it a correct initial guess, it's really good. So it doubles this number of digits every time. That's this feature that it has. Okay, so good. So this was all about algebra and arithmetic. So let's now turn to a very different thing. Okay, so to a puzzle. So this is like an interlude or something. So here is the puzzle. The puzzle is how many guards do you need to cover all galleries in a palace? Okay, so this is like okay, what palace, which galleries, etc. So here is what our galleries and guards, let's say, look like. So this is our sort of schematic palace. So these galleries are these pink lines. Okay, and where the white dots are, that's where you can potentially put guards. You can put a guard at any one of the, like as many guards as you want, but the guards have to be on the white points. Okay, and when you put a guard on a certain point, all the galleries that are incident on it that it's looking at, they get covered because someone is looking at those galleries. And the question now is how, so given such a palace, a description of a palace like this, how many guards do you need to put to cover all the galleries? Okay. So you want to put as few guards as possible to cover all the galleries. So we can play this game. So let's say, where should I put the first guard? Good, yeah, that's a good. So where this sounds good. Okay, let's put this. So okay, so these guys got covered. Okay, what should we do next? Okay. Okay, good. So already we are coming up with general principles, right? So this is the general principle that you first pick up the position which will cover the maximum number of galleries. Then of course some number of galleries are covered. So now you'll pick up the position which covers the maximum number of galleries, except that you don't count the galleries that are already covered. That's what you meant, right? Yeah, and you keep doing this. Okay. Do you think you'll always find the minimum number of that? You know, do you think that it will always be within, so like, so if the, let's say if there are always, like say, some number of guards in here, this will find something that is close to that? Yeah. How close? Sorry. Okay. Uh, so yeah, so this turns out to be a very natural algorithm. It turns out to be actually harder to, yeah. So this is an algorithm, like a procedure. So that's word, but but it turns out that there's another process that you can actually show uh, does, I mean, it does not actually necessarily get to the best assignment, but it gets reasonably close. And you can say how close without knowing what the best assignment is, without knowing what the best positioning of guards is. So let's try to do that. And that process, I will tell you, is this. So the process is, it's very similar. So instead of taking this maximum sort of the guard who covers the maximum number of vertices, so it's like greedy right away. So like you try to greedily pick the guard that is who is doing the best currently. But the reason it might hurt is because maybe by choosing some other guard you would have potentially saved in the future. And here is the process that does not suffer from this. And the process is that you pick a guard. So or rather you don't pick guard. What you do is you pick a gallery that is not yet, as long as possible, you pick a gallery that is not yet covered. Okay, so let's pick any one gallery. So let's say we pick this gallery, and you put guards at both ends. It looks like a strange thing to do, but you put guards at both ends. Okay, so that gallery is certainly covered, but some others are also covered. Now you again try to find a gallery that is not covered. Okay, and you again put guards at both ends. So again, so let's say which gallery we pick. Let's say we pick this one. Okay, then let's again pick one more. Which one? Oh, did I? Oh, sorry. Yeah, so I should not do that. Yeah. Okay, this I don't need to pick because anyway, it's not going to cover anyway. So I'll break my rule and not do that. Yeah. Yeah. Which one? Go back. Yeah. Yeah, instead of picking the guy at the bottom, you can pick the guy at the top. This one? No. The one to the right of This one.
That's the gallery opposite.
This one.
Yeah, he's a guard opposite this guard, but he is connected to other.
Okay, and this one. Okay, this is what you wanted. Yeah, sure, yeah. I mean, yeah, we can keep doing this for a while. I mean, I'll put this link online so you can play this game to your heart's content. I mean, this one I won't pick because it's anyway covered. But okay, sorry, I again broke my rule. Sorry, what did I do? Yeah, this and this, and again I don't need to pick that one. This. Okay, so I took 12 guards and I followed the rule. What I can tell you is that no one can do better than 6 guards. Doesn't sound very nice, right? I mean, I did 12. All I can tell you is that no one, because I followed this rule of mine, no, or not mine, but like a well-known rule, no one can do better than 6 guards. No matter how clever they are, 6 guards will be needed. Okay, and you can do this on bigger, more complicated palace. I'll put this online. So here is our rule. Our rule is to pick an uncovered gallery if there is one, put guards at both endpoints of the gallery, okay, and repeat this until all galleries are covered. Okay, and here is a claim that if you, while doing this, have to put G guards, so G is some number, then no one, no matter how clever they are, will be able to do anything better than G by 2. Okay, why is that? Let's try to see. Let's try to prove that this is the case. Yeah. Yeah, that is true. But there's also another thing that no one else can. So no one else can sort of do any parallel processing. So in the following sense. So let's say I follow this algorithm and I do it arbitrarily. There is no cleverness at all. So for example, Arna was trying to tell me to be clever about it and pick this one. I don't need to be clever. I will just use this policy. Whatever I get, the correct answer will be at most half, or at least half of that. And the reason is the following. So let's say I follow this thing in any way I want. I pick any, whenever I have to pick a gallery, I pick any uncovered gallery in the most brainless manner as possible. What is going to happen is the following. Let me look at the list of the galleries I picked. Okay. Is it possible for any 2 galleries in this list that one guard can cover both of them? No, that is not possible, because these galleries are always, so you pick a covered, so you pick a gallery and you cover both ends, right? Any other gallery, therefore, that you pick later on will need 2 guards that are not among any of the previous ones that I mean, the guards that are covering the previous ones cannot cover this. Okay, so the important thing about this list, which is similar to this point of building redundancy, is that in a list that you pick in this way, any 2 galleries that are there in the list, they require 2 different guards. So if you have picked k galleries in this algorithm, anyone, no matter how clever they are, they have to pick 1 guard separately for each of these. So they have to put at least k guards, and you put 2k. So you are never worse than half, or worse than twice. Okay, and no one, no matter how clever they are, can do better than half of what you did. Okay. Yeah, this doesn't look like a very good approximation, right? So let's see that. So this, huh? So let's see. So this is called a so-called a 2 approximate solution. So you could not find the best, right? I mean, if your business is to operate museums and their security, yeah, if the optimal answer was to hire G guards, your method will hire maybe 2 G guards. So it's 2 approximate, right? And no one knows how to do it at 1.99. No one. This is I mean, there are some things that are slightly better known, in the sense that if you have a lot of guards, then it will be 2 minus something like 1 over some number that depends upon how many, there's lots of galleries that are there. But if you want to say 1.99 times the best, not known. Okay. And in fact, widely believed, among, like, I'm not an expert on this, but the experts in this area would believe that you cannot do it. 2 should be the best. What we know is that if you could do it better than something like 1.36, then crypto systems will be toast, in the sense that your the things that are used to run your credit card, banking, etc., UPI things to keep them secure, those will be broken. So there will be algorithms to break those. If you could do this with 1.36, that is known. But people believe that even 1.99 should be able to do that, but that's not something that has been proved so far. So mathematical immortality awaits anyone who can either give a 1.99 approximation or show that 2 is the best possible, essentially best possible. Okay. Yeah. So okay. So yeah. So this I didn't want to go to. So this is, yeah. So the question was, what is the connection of this to cryptography? So the connection is the following. So have you heard of these so-called NP hard problems? Yeah. So okay. So yeah. So there are these whole class of problems called NP hard problems, and in fact, more precisely, something called NP complete problems. So these are problems where if you solve any one of them efficiently, all the others will also fall, right? And none of course, therefore, no one knows how to solve any one of them. This is one of them. Okay. So this is one of them, and it is known, in fact, that even solving it to 1.36 is one of them. Now, what is the connection to cryptography? So a lot of cryptography, so things that are used to secure, like, so when you see this green dot on your browser, right? Like often you're told that, do not interact with the bank website until you see that green lock, etc. So that green lock, the way it is done, the reason it is supposed to be like secure is based on an assumption, and the assumption is that no one can factorize large integers. So that is one of the assumptions. Now, factorizing integers is not known to be NP hard or NP complete, but it is slightly easier in the sense that if you could solve any NP hard problem, this would also have an efficient solution, and therefore, yeah. So that's the okay. Yeah, so this one is just one, but almost any optimization problem you come up with in real life, I mean, unless you're extremely lucky, and like there are some case situations which are lucky, but it turns out to be NP hard. So, for example, okay, so this is covering thing. Almost any kind of constraint satisfaction, where you sort of say that like classroom scheduling, right? If you have things like, I have a bunch of rooms and I will have a bunch of classes, and there are some conflicts that these two classes cannot happen together because there are students in it. So these kind of questions where you have some constraints and you want to find the best solution, unless you're lucky, turns out not to be NP hard. Yeah, I mean, yeah, these kind of constraint operations. So what? Yeah, under certain constraints. So that often turns out to be NP hard. So what you have to settle for is some kind of approximation. So some guarantee that okay, whatever will happen will be not so bad, etc. Okay. So okay. So any questions so far? No. Okay. Yeah. So as I said, mathematical immortality awaits anyone who can get anything better than 2 here, or show that 1.99 is not possible. Okay, so far we have been looking at approximation as something one has to live with. We cannot do the exact thing. Maybe it's too hard, or takes too much time, or too costly, and so we do approximation. But sometimes you actually have to do approximation just to be correct, and being exact can actually lead to errors. So let's see an example of this, and this will be a slightly whimsical story. Okay, so apologies, it's too whimsical. Okay, so here is the story. So there's a usual prologue a long time ago in a galaxy, etc., etc. So Spacey Puravedi was wondering what effect including the terracity of a spaceship has on its space. All fans of science fiction know that these are all very well-known terms, right? Like everyone knows the definition. No one knows that stuff. So these are just invented terms. So just like usual science fiction. So this person, Spacey Puravedi, is wondering what effect increasing the terracity of a spaceship has on its spacage. Yeah. A very well-defined problem and so on. So what does Spacey do? So Spacey has paid attention in school. Okay, so in particular in the science class. So Spacey knows that if you want to predict, so if you want to predict whether increasing my teracity by this much will increase my spaces by that much or not, the first thing you should do is actually measure what happens. Like, so he measures, okay, and he plots. Like this also he has learned in the school that you should try to do plots to see what relationship are there between various variables. So he finds some data that looks like this. Is this visible? The dots are visible, right? So you can see that there are these kind of dots. So the teracity increases like this, 2, 4, 6, 8, 10, and the space edge. And by the way, he also knows that you have to mention units. So he has mentioned the units, standard units. Okay. Okay. So, so this is the data he gets. So at this point, he recalls some more things that he learned at school. In particular, one thing he learned was fitting straight lines to data. So this people must have done, like finding G by looking at the pendulum time and so on, and finding resistance by looking at voltage, current curves, and so on. So yeah, so he remembers at least some vague recollection of this. He says, okay, let me try to fit a line to this, to draw a line that sort of fits this data. So he plots a line, and this is what the line looks like. Okay, and at this point, he says, but this looks so approximate. I mean, this line is like not passing through almost any of the points. I mean, one point is on the line, but everything else is off the line. I mean, what is this? I mean, like in this age, do we have to settle for approximation? So Spacey is lured by the promise of exactitude. So this is a story with a moral. So this should happen. And so Spacey jogs his memory and searches the space net and all these things, and he has a shiny new computer, and he remembers that why straight line can fit his data to polynomials. So polynomials look like this. So everyone knows, yeah. So polynomials are basically, yeah. So you are not just proportional, but you can also do squares and cubes. Okay. So now he has an exact fit. Okay. So he has fit the data exactly. Like every point is on the line. Okay. And all of this is done correctly, by the way. Like this is all done using the state of the art tools. All correct. Okay. Yeah, that you have to ask the tool. I try to optimize it, find the best fit. And, yeah. Okay. Yeah, actually not the tool. Yeah, I'll say what. So success, right? So now Spacey goes forth and predicts, right? I mean, that was the original goal. And here is the prediction. So the green part is a prediction. So that if you increase the teracity anything below above 10, then the spaces just jumps. And wow, very happy. But maybe Spacey has now at this point reality struck. I mean, clearly the spaces is such a important resource. It can't just be available for free, right? So something has gone wrong. So Spacey at this point now recalls some old lessons about the perils of something called overfitting. And this maybe is a word that maybe you hear more often these days because of all the ML and machine learning things that have been going on. So this is what has happened really is that in trying to fit exactly what Spacey has done is he has learned the noise. He has fit the noise in the data. There was some noise, maybe due to measurement, maybe because the spaceship had some issues and so on. And all this noise has been fit. Okay. And but still a doubt lingers. Maybe this polynomial is the right answer. Maybe spaces does increase badly, like really, like it goes off the charts, and the line is not the right answer. So how does one check that? I mean, Spacey has only this much data. Making more measurements is costly. I mean, already like the people at the spaceport are complaining and so on. So what should Spacey do? What's so something much more uh, like much more commonsensical. Yeah. So one thing it can do is that it can not try to fit using all the data. Okay. The answer should not use all the data. There's no outliers, right? In this data, I mean, this data does not look like it has outliers. Like everything looks reasonably fine. It's not clear how to say anything is an outlier. Okay. So yeah, so that could be a problem sometimes, but here all the data looks reasonable. Yeah. Sorry. Yeah. So yeah. So one thing one can do is to not use all the data. So it's somewhat counterintuitive. Do not use all the data. You have all the data, but ignore some of it. Okay, but do what with it? So when you train, so when you fit your model or when you find this line, do not use all the data. Whatever data is left out, you use that to test or so-called validate what you have learned. Okay. So now Spacey does this thing. So some of the points are now deleted. So there were 10 points. Now 4 of them have been thrown away, and he only has left the 6 points. And again, he does both things because he wants to check which the line of the polynomial is the correct answer. And now he gets a slightly different polynomial. Already they should say that, okay, because this is a problem. If the polynomial is changing too much by if I threw in some data, that's already should be a red flag, right? If it was a correct answer, they should not have changed because I just threw out some data. It should not have changed so much. But something more quantitative can be done. So if it's both the line and the thing, again this polynomial fits perfectly the line, like nothing lies on the line almost. But then what he does is he checks the predictions. He tries to predict on these held out points. These points that were held out, tries to make predictions on that and see which one is giving a better answer. And here is what he sees. Right. So the polynomial is just off the charts, literally. Line is here, the held out points are here. So the polynomial is so off the charts that the line that was like this has become horizontal. So really what is going on is something like this. So it's zoomed in onto the correct part. So the line is there where it was. It is sort of doing reasonably well. Polynomial is just going off the chart. Okay. And so Spacey learns that approximating sometimes is indeed the way to go when you are trying to predict in the presence of noise. So here, approximation was crucial. If you try to do exactly, you would make a mistake, a serious mistake. You would not be predicting properly. And this underlies almost every application of statistics, machine learning, etc. You have to be very careful about this over parameter, like having too many parameters to fit. The funny thing is, so this is the end of our story. But the funny thing is that this phenomenon, I mean, yeah, we are talking about machine learning, statistics, all this. This has been known for a while. In fact, it has a name. It's called the Runge phenomenon, Runge. It's a German mathematician. And he, in fact, said what usually happens. And this is exactly what we are finding here also. Say that if you try to fit high degree polynomials or these polynomials with a lot of terms to data, which is sort of has some noise, then there are lots of oscillations near the end points, which is what you're seeing. So this is, so you had this question, right? That why is it that here it is trying to move like this, that it's going really far up. This is a more general phenomenon that happens very often. That when you try to do this kind of fitting with a polynomial with large number of parameters, it's the behavior is worse at the endpoints. And again, a lot of effort has been, because sometimes you do have to fit polynomials or things like that. So you have to figure out ways to ameliorate this. Okay, so that is also another interesting, very important field of study. That's a story for another day. So any questions about this story? Yeah, so again, so these are all like at this point it becomes like so what I did here was 40-60. It's the standard thing to do 80-20, but again, these are all rules of thumb. But I mean, the thing is that if there's a problem, you will detect it already in one of the precise number, isn't it? No, so yeah, so okay, so okay, yeah, that's a good question. It's a very good question. So you could do two different things here. For example, one thing you could do is to drop points at random. What I did was to drop points at the end. So this again depends upon what you are trying to do. So if you're trying to, for example, predict the future, I mean, in this case, it's not really future or past, but if you're trying to do some kind of prediction for the future, then it maybe makes more sense to remove the points at the end, because what you're trying to test your model is given the time data till some time, say till today, can it predict tomorrow? So what you will do is maybe train till day before yesterday and see if it could predict yesterday. Right? If it is not, if there's not such time ordering, then maybe it's better to remove things at random. So I'm sorry. Okay, so from the world of Spacey, let's come back to our own nook of the universe. So this is the last part of the talk, and now let's look at the motion of planets. So, so imagine that you are in ancient Greece or ancient India or ancient Iran or ancient Arabia or something, and in the night you look up at the sky and what you want, and you notice that there are lots of patterns, and it's very beautiful. And of course, there are no lights right at that time, so you actually see the sky, unlike now. So you see a lot of patterns. So one thing that often we forget because we don't see the sky so often is that there is this old ancient notion of so-called fixed stars. So basically, the thing is that if you, of course, if you just keep staring at the sky on a particular night, all the stars will look like rotating. So from where we are, we'll see that they are rotating around the north, the Polaris, the pole star or Dhruv Tara as it is called. So that will look like as if it's fixed and everything else is rotating around that. So this, of course, is like a motion that is just there, right, every day. So you would want to remove this motion. So you'd want to think of this as, okay, these stars, they don't change in their relative positions with each other. So let's say that they are fixed. But then you find that there are other bodies that keep moving with respect to these stars. So of course, these stars also move, but in a one human lifetime, you don't see what is going on there. So let's say those are we treat as fixed. So, but there are other things that seem to move even in on a like at least even on a monthly or annual basis. So these things are called planets, and that's where the name comes from. I think it means wanderer or something. So these things, and they look like as if they are moving against the stars. If you even if all the stars were fixed, their relative position with respect to the other stars is changing, like from day to day, from year to year. The sun itself has this feature. So if you just plot, in fact, this is how people would do these things in the end. Of course, you can't look at the sun in the day. So around the time of sunrise or sunset, you will see which are the stars close by when the sun set. And when if you keep plotting this, this keeps changing. That's what the zodiac or etc. is, right? So you keep changing throughout the year. So what you do is you then plot the position of the sun with respect to these stars throughout the year. So if you do it with the sun, and remember you are in this old era, you end up with a picture like this. Okay, so you see, so let's wait for this. So there's this circle, and let's just, yeah. So you see, so there's some kind of a circle on that is described on this big sphere of the stars, and the sun keeps moving very regularly on that. This is a lie in the sense that if you actually did it for a few thousand, I mean, only 10,000 years maybe, you will see some deviations. But at at the level of a human lifetime, you don't really see any such deviation. Okay. So you see nice circle. Okay. So then now you're very encouraged. So you try to do it with one of your favorite things, like the other object in the night sky that is very prominent is Jupiter, very shiny planet. So you try to do that with Jupiter, and now this is what Jupiter thing looks like. So let's wait. Yeah, you see a red dot. So yeah. So does anyone recall this from school? This is actually I think it's certainly taught in school. It's called retrograde motion of planets. So what is going on? Yeah, it moves forward and it keeps moving backward. Then again it shoots forward and then again. By the way, this is again a real thing. It's like I did actually compute the position. Like, yeah, I mean, there are now easily. It's not as hard to do as. So okay, so I should. There's another story here. So I think so. I don't know how true this is, but it is believed that, or at least some people claim that when Tycho Brahe, a Danish astronomer, was plotting out the orbits of all the planets, like in excruciating detail. This I think in the 15th, 16th century, something like that. This is what led to this is data that was finally analyzed by Kepler, who came up with these Kepler's laws and like, really established heliocentricity as the right model. Um, apparently, at that point, this whole operation of Tycho Brahe was a significant fraction of the Danish GDP. Okay, so today, of course, you can on a laptop plot these positions. I mean, it's that simple. But yeah, at that time, like this was a serious business. So okay, but yeah, but you had these things, and you wanted to explain this. So 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 of course, if you're in that era, and I don't know what was happening in India or the Middle East, but at least in Greece and Rome, um, some kind of uh, maybe conflict or something of things were happening that what you really wanted to believe is that the Earth is the center and things are moving around it. But this looks like then Jupiter is doing all kinds of weird things, right? I mean, it's going forward and backward and forward and backward, and it's kind of interesting. So one of the two of like, so the question was how does one predict this? And Apollonius and Ptolemy, both very smart people, like a lot of other things named after them. So they derived a very beautiful approximate solution to this, while working mostly within the confines of geocentric circular orbits. And it's funny because if you look at it today, it looks like they're almost pretending as if they, so it's like as if they knew that, you know, you want to put the sun at the center and do everything, but they're pretending as if no, we can't do that. Let's do something. But any case, but here is a very beautiful solution. So 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 in fact their solution is so interesting, so nice that it can even handle other complications, like the orbits of the planets are not actually circular even around the sun, right? So even that their method can handle, but let's assume for now that orbits are circular, and let's simplify the picture a little bit so that it's not, there is no sphere, it's like on the plane. So here is what they see, what they would have seen the movement of Jupiter like, right? So it's sort of almost on a circle, but like going like this. Okay, and what really is happening, which we know today, because so what is really happening is something more like this, because it's actually going farther out and back in, farther out and back in. Of course, at that time, I mean, Ptolemy did try to compute distances, but they are not very accurate, and it's hard. I mean, like it's hard to compute this distance to the planet, so he could not actually see that the distance to Jupiter is also changing. Could only see the direction, right? These people can only see the directions. So this is what was happening, and here is the solution they came up with. And the solution, it's like, it's kind of amazing in its sort of simplicity. It's like it says that there is something that is moving along a circle, and then there is a smaller circle, and Jupiter is actually moving on that circle. Okay, so there's a circle within a circle. So these things called epicycles. It's a pretty good model. It can, I mean, as you can see, in the circular orbit case, it's exact. It's actually, in fact, I cheated a little bit. The previous picture was generated from exactly this one, and it's correct. Like if the orbit was circular, this is what will happen. It would be exact. Okay, but it is powerful. It can handle these other these things like elliptical orbits also, and Ptolemy could do that at that time already. Okay, and this is like first century CE, I think, or second century, something like that. So yeah, so this is quite nice. So these epicycles are powerful, and there's some kind of approximation. And Ptolemy is already handling complications to the elliptical orbit, etc. So you're just moving the center a little bit away from the Earth and then do it. Okay, so what is today? So today, this is not surprising, because what you can do is you can see epicycles as, again, a special case of a much more general thing called Fourier analysis. This, in its current form, is due to Joseph Fourier, who was funnily a French military engineer. So he was in the military. And the principle there is actually is probably familiar to different people in different ways. So for electrical engineers, it's like saying that every signal can be decomposed into a combination of periodic signals. For musicians, like all sounds can be decomposed into a combination of pure tones. So, you know, like pure tone is like fixed frequency tone. Everything is a combination of those. Stated this way, it looks like a triviality, but it's really like but when made precise, is a very, very powerful tool. Okay, so it's so powerful that it lies at the heart of very many things. In fact, the way this video is being sent is using this. So JPEG, MPEG, all of these compression techniques are based on the Fourier transform, or at least a special case of the Fourier transform called the discrete cosine transform. Signal processing, other signal processing applications such as noise cancellation, noise removal, all of these things. In fact, I mean, I didn't put on the slide, but I can say it. I think it's probably hard to find a field of science where it is not useful. So almost everything, there is something or the other where you will use a Fourier analysis to remove noise or find the right part of the data and so on. I mean, you could use it on like things like weather or financial data to see if there are alien periodicities. I would not do it here, but like there are things. Well, in like 1800s, I don't know how you are electrical engineer, but yeah, like early 1800s, but to the extent others, yeah. Yeah, he was maybe a few century too early. Yeah. Yeah, so it's a fundamental tool in many other branches of mathematics, physics, computer science, and like yeah, even in pure mathematics, there are like fields that are devoted to sort of generalizations of this representation theory. Okay, so that is essentially the end. There are many other aspects of approximations that we did not cover, and many people that we did not cover. There are some written here. Chebyshev, another giant. Ramanujan is like probably best. Like among some of his more intriguing things are like finding these formulas for pi which converge really fast. Like some of the fastest known were due to him even till 10-20 years ago, a few decades ago, and then they were improved. Madhav of Sangamgram, who was was a, I mean, he had a school of things, and what they were doing is, well, sure. So this is again a question that was asked. Like you have an approximation like this Newton-Raphson. How good is that approximation, and can I add some other term to make it better? So they were working on general things of this kind. Again, more or less, they developed many parts of the calculus before Newton and Leibniz. There's an amazing thing of something called infinite continued fractions, uh, which it's amazing because what it does is that for questions like this, like what are the best rational approximations to root 2? What are the, I mean, I want to write root 2 as a rational number, so a by b. What are the best a by b I can choose? Sort of gives you all the solutions in one go. So and the funny thing is that continued fractions are first, at least some form of them were first discovered. Uh, I think by probably the first is Brahmagupta while he was trying to solve a, something called a Diophantine equation. I mean, he of course didn't call it Diophantine equation, but the funny thing is that the function, the thing you're solving, it's called Pell's equation. It's kind of funny because Pell was born 1,000 years after this, but and these people had solved it before, and Diophant was already studying it 1,000 years before them. But yeah, so so they give you these best approximations, and then there is also this new thing that is coming up. It's called weight quantization. So you might have seen all these large models and like billions of parameters and these many trillions of parameters and whatnot. What are these parameters? We have numbers, right? And they have to be stored somewhere, right? So if you do any kind of numerical computing, especially in physics kind of applications, by this time you have been taught to use so-called double precision arithmetic, which means that basically all your numbers are stored with 16 digits of precision. Okay, uh, the machine learning world is usually going in the opposite. Things are usually to 8 or 9 digits, and the reason is that if you store 16, then your size of a model will double. So you will need 2 times as many GPUs and storage and so on. Right. So then the question is like, by even while keeping these number of digits small in the parameters, can you still get good performance? So that is often referred to as this. So there are several stories of this kind for another day. So with that, I just say.
Okay, just one second. Are there any questions on the net? Folks who are online, this is your last chance to put your questions in the chat and we will try and take them. I don't see any questions. Yeah. Okay. Yeah, go ahead. We'll just give it a few minutes and then shut it. But till that time, you can ask. Can you give an indication how the exercise was related to the 4-year?
Yeah, so you just write down the equations and you'll see that they're basically like what you're doing is that they're two different frequencies. So in this case, it's actually fairly exact. One of the components is the period of Jupiter around Sun. Yeah, so that's the thing.
So you are saying the position now?
Yeah, yeah. So you just decompose, let's say, the x coordinate and y coordinate separate. Yeah. The line cannot hit the assessment. Yeah, good question. Yeah. So as I said,
so I wanted to ask you. I mean, do you assume it's differentiable?
Yes, yeah. Twice differentiable. In fact, in many cases, yeah.
Okay, one second. Let me shut down the live stream.
sometimes twice.